Hi class, welcome to our next section. We're starting a whole new chapter, chapter 10. Chapter 10 you can kind of think of as an introduction into linear algebra. You can kind of think of chapter 9 as an introduction of linear algebra as well. In this chapter we're really going to focus on matrices, right? In order to start that discussion, however, we're going to start off with systems of equations. In the next section, we'll talk about larger systems. In this section, we're going to focus on systems in two variables. So it'll be two equations in x and y. In the next section, we will have larger systems of equations that we'll be dealing with. And then we'll talk about how these things relate to matrices. Okay, so let's go ahead and get started. So a system of linear equations is basically more than one equation. Each of those equations have more than one variable present. So typically we're interested in, ideally we would have the same number of equations as we do variables, but that doesn't always happen, right? So in this section it'll be two equations, two variables. Generally what happens is that each equation represents some different characteristic of whatever situation you're trying to model. Okay, so for example, if you were using a system of equations to model production, you might have one equation that models the cost to produce a certain item, right? One equation that models the number of items that can be produced if you are buying this amount and this amount of items, right, of material. One equation that models the revenue that you generate by sales, etc., right? So you have all of the variables represent the same thing in these equations in this system, but you have different equations to model different characteristics, different aspects of your system as a whole. Okay. So again, all of these will represent different characteristics of the same situation. So again, we're going to stick to two equations with two variables each, right? So A, B, E, C, D, F, those are all our coefficients. X and Y are our variables. So this should look semi-familiar to you. Again, if you have ever taken an algebra class, this is something you study quite a bit in algebra. We're just going to kind of introduce it now again, and then we're going to expand on this idea throughout this chapter, right? So each of these represent a line, okay? So I can solve this for y, and it'll look like basically y equals mx plus b. So we've seen lines before. Now we're putting them together as systems, right? So again, these are two lines in R2. There's a number of ways. There are only so many ways that you can put two lines on a graph in R2 and have them interact differently with each other, okay? One of those is that if you put two lines on the same graph, that they're going to intersect each other, okay? And here we're sticking specifically to R2. We're not in 3 dimensions anymore for right now, right? So if I put two lines on a graph, one option is that those two lines will intersect somewhere, okay? And they're only going to intersect once, right? And that point where those two lines intersect are when the two lines are equal to each other. We've covered this before back in chapter 2. And that is the solution to my system. The solution is when the point where those two lines intersect, where they have a shared value of x and y, right? That's my one solution. Another option is that we put the two lines on our graph and they don't intersect at all. And the only way for these two lines to not intersect at all is if they have the same slope but different y-intercepts. They're offset by a certain amount, but they point in the same direction forever and ever, like two railroad tracks, right? So the only way for them to not intersect is for them to be parallel, and since they never intersect each other, there is no solution. There is no point that is shared on this line and this line also. Okay, there are two separate lines and they are parallel to each other and never will intersect. The third option is that one line lies directly on top of the other, or that another way of saying that is that they are the exact same line, okay? In this case, they share every point in common, And so there is an infinite number of solutions because every point on one line also lies on the other line, right? And those are our only three cases in 2 dimensions, is that we have either one solution, we have no solutions, or there are an infinite number of solutions. There are no other options, right? Meaning that I can't, for example, have 2 points where these two things are the same, because it has to be one, none, or all points, right? So you'll either have one where all points will be the same. You'll never have 5 points in common between 2 lines. It does not work that way, okay? There's 3 methods for solving a system of equations in R2. One method is to graph the 2 lines, just like we kind of did here. Well, in all 3 of these cases, but graph the 2 lines and find their point of intersection. That's one way to find their solution. Another way is what is called the substitution method, and the third way is called the elimination method. We'll go over all 3 here. So what we're going to do is we're going to look at one example, and we're going to solve it all 3 ways, and we'll notice that through all 3 methods, we always end up with the same answer, because obviously if we have a solution, there's only one solution, or none, or infinite, right? So let's say that we want to graph. The way that we do this is, again, we just graph the 2 lines and find where they intersect. The substitution method, you take one of the variables, one of the equations, and you solve for one of the variables. It doesn't really matter which variable you solve for. You can solve for x or you can solve for y. Once you have solved for a variable, you take that equation that you solved, right, and you plug it into the second equation. Then you just solve for the remaining variable that you have. The elimination method, what you want to do is you want to get your coefficients to have the same value. Ideally, you want them to have the same value, but be opposite in sign. And then what you do is you add the 2 equations together once you have made the coefficients the same. And the way we make the coefficients the same is by multiplying the equation by a constant value. Multiply every single term in the equation by a number. Once we have that, we can add the 2 equations together or subtract them, and that variable will then be eliminated because it has the same coefficient. And then we take that remaining variable, we solve for it, and then substitute it into either one of our equations. So that sounds like a lot, but once we do an example, it'll make sense. So let's go ahead and start off with an example. So let's consider the system 3/4 x plus 1/2 y equals 5, and negative 1/4 x minus 3/2 y equals 1. So I decided to try to choose the one that was the most confusing for us to work with, because if we can do this, then the ones that have all whole numbers will be way easier to deal with, okay? So we have the system. The first thing that I'm going to do is I'm going to solve it by graphing. So I'm going to graph this equation and this equation and find where they intersect. I can graph in 2 ways. I can graph by finding the x and y intercepts of this and plotting those and drawing a line between them and doing the same thing here. Or I can solve this for y and solve this for y and have it in the y equals mx plus b form and then graph it that way. So that's probably the easiest way, because that's the way we've been doing throughout this entire textbook, is just solving for y. So let's go ahead and do that. Okay, so I'm going to put them in the mx plus b form and plot my points. So I take my first equation. I will go ahead and clear the denominator. So if I multiply everything by 4, I don't have any more fractions. So I'll have 3x plus 2y equals 20. So multiplying by 4, the 4's cancel. Multiply by 4, I get 2. Multiply by 4, I get 20. Now it's a lot easier to solve for y. I'll subtract the 3x, and then I'll divide both sides by 2. So this equation inside of in the y equals mx plus b form is y equals negative 3/2 x plus 10. If I do the exact same thing here, I'm going to clear the fractions. So common denominator is 4. I multiply everything times 4. So this will be negative x minus 6y equals 4. I will add x and then divide everything by negative 6. Okay, so I get y equals negative 1/6x minus 2/3. So I'm going to graph this line and graph this line. I'll find the y-intercepts, apply the slope, right? Down 3 over 2, down 3 over 2, down 3 over 2. Same thing here. Start with my y-intercept, go down 1 over 6, down 1 over 6, etc. And this is what my graph will look like. Okay, so I start at 10, down 3 over 2, down 3 over 2, so forth. Same thing here. I can graph my y-intercept, my x-intercepts, whatever it is I need to do is fine, but both of these lines meet at the point 8, negative 2. That's the point of intersection, right? 8 and negative 2. So you graph each line, find where they overlap each other. Okay, so next let's go ahead and solve using the substitution method. So real quick, notice that I've already solved this for a variable, right? So I could take this y and then plug it into this equation here, negative 1/4 x minus 3/2 y, and then just plug this whole thing in. But I still have a lot of fractions, and that's kind of a lot of work. So notice I've solved this for y, and I've solved this for y. So really what I can do is just set these two equations equal to each other, which is what I'm actually going to do. So if we want to solve by substitution, again, note that we already solved both equations for y. So y equals this, y equals that. That means they have to be equal, right? If y is this, y is that, well, they're both y, so they're the same thing. Set them equal. Okay. So most of the times that's not what we have to do. Most times we just take one equation and solve for x or y and then plug it in. Here we've already done the work, so we'll just move forward, right? So I set one of my y's equal to the other y. Notice now this is not two equations, it's actually one equation because there's only one equal sign and there's only one variable. So if my number of equations match my number of variables, I can always solve. So if I had this and I still had a y in here somewhere, I couldn't do this, right? I wouldn't be able to solve at all. I have one equation, one variable. I can get x on one side, all the numbers on the other side. That's my goal. I could add 1/6 to the other side, but I don't like messing with fractions, so we'll clear the fractions, right? Common denominator of 2, 6, and 3 is 6, so I'll multiply everything times 6. That will give me a negative 9 here. That'll give me 60. This will be a negative x, and this will be a minus 4. Okay. There we go. So multiply everything times 6, and all the denominators will go away. Now I can move everything over, get all of my x's on one side, all of my numbers on the other side. That'll result in negative 8x equals negative 64. They're both negative. You can just make them positive, or if I went the other way, they would have turned out positive. So x equals 2. Okay, 8. I'm sorry. I'm sick. You can hear it. X is 8. Now that I have a value of 8, I just pick one of these equations to plug in for my x, right? I can put 8 here. I can put 8 here. Probably makes more sense to plug in 8 here because 8 over 2 is 4, right? 4 times negative 3 is a negative 12, plus 10 will give me a negative 2. Okay. So this will be the easiest one. This gives me a negative 12 plus 10, negative 2. Therefore, my solution is at 8, negative 2, which is exactly what we had from graphing my two lines. Okay, surprise, surprise. So now let's talk about the elimination method. Okay, so if I want to solve by elimination, I want to get the coefficients for either both of my x's to be the same or the coefficients for both of my y's to be the same. And the way that I do that is by, in my original equation, multiplying this whole equation by some number and this whole equation by probably a different number so that the x's match up or the y's match up. So for instance, if I wanted to, if I multiply this whole thing times 3, this would be 3/4 and this would be negative 3/4. I can add them and the x's would cancel. Okay, that's not what I actually do here, but I could do that right away. That's actually pretty nice here. I didn't notice that until just now. Okay, so this would be 1/2 plus a negative 9/2, right, equals 5 plus 1. So that would be plus 8, right? So then right away I could just solve for the remaining y equals what have you. But I've already cleared out the denominators here, right, in here. So I'll just use those two equations. I'm going to use this 3x plus 2y is 20, and this negative x minus 6y equals 4. And I'll just use those because I've already multiplied them by something to have an equation that's easy to work with. Okay, basically does not have a bunch of fractions. So we've already seen this before. So here I clear the denominators on top, clear the denominators on the bottom, and this is what I get out. Here, same thing that I was thinking of before, multiplying this by 3. If I multiply this bottom equation by 3, my x's will match up. That's the easiest way to do it, because if I try to get my y's to match up, well, I could do that. If I multiply the whole top equation by 3, I have 6y and minus 6y. So I could do either one of these by 3, and I'll either get the coefficients on x to match, or I'll get the coefficients on y to match. But let's go ahead and do the bottom one and multiply it by 3. Okay, so 6 bumps up to 18, 4 to 12. Notice that my x's are both 3's and they have opposite sign, so I'll just add them together. Okay, and what I get out is negative 16y equals 32. So I solve for my y. Okay, that gives me negative 2. So now I take this negative 2 and I can plug it into one of these equations or one of these equations. It doesn't really matter. Normally we plug it into an original. In case we made a mistake getting here, then we're not making a bigger mistake. But it doesn't matter. As long as my work's good so far, maybe the easiest one to plug it into is into this bottom one. Okay, so I have negative x minus 6. Y is negative 2 equals 4. This is negative x plus 12 equals 4. Minus 12 on both sides is a negative 8, and then change the signs, right? So you guys can do the math here, but we get the same number, same exact value that we had before. So all 3 ways gives us the same answer. Okay, so generally elimination is the method that we try to tend to stick to. Okay, so let's say that we ended up with something like 0 equals 2, right? So let's say like I came here and I got my x's canceled and my y's canceled, and I end up with a 0 equals 32, right? Or 0 equals any number, really, right? But if my x's and my y's both cancel out from here, or maybe when I'm trying to do my substitution, I move my x's over, right? Maybe I actually have negative 9x and another negative 9x, and when I move this over, I have no more x's and just constants left over, right? So I have 0, I would have like 60 equals negative 4, for instance, right? Basically, if I ever end up with something that's not true, like 0 equals 2 or 5 equals 3, then it's not that you did something wrong, but that there is no solution, okay? It ends up being that we are in the situation where my 2 lines are parallel to each other, okay? You end up in this solution when you come into a false statement. So again, if you get something like 0 equals 3, or something like 1 equals 12, right? You didn't mess up. There's just no solution. You derived it down to a false conclusion. So there's no solution there, okay? If you come across what's called an identity, something like the x's and the y's do cancel all out, but you get something that's true, like 2 equals 2 or 12 equals 12, then what happens is that those 2 lines are the same line and you have infinite solutions. Okay, so if you run into something that's not true, no solutions. If you run into something that's always true, then it's infinite solutions. And if you run into a specific value for y and then a specific value for x, that's your solution.